Now I wanted to show you guys how to combine impedances that are in parallel. So let's say we have a circuit that looks like this. So we have a voltage source, we have a resistor, and the resistor is in parallel with a capacitor. So we have not seen this before. And let's say, instead of being given values for these, let's just, let's say we have a 1K resistor, but instead of worrying about what the capacitance and what the frequency is, we'll just say that whatever combination these are, these give us a capacitive reactance of 2 kiloohms. Okay, so so we know that this circuit is equivalent to a single complex impedance, some equivalent impedance to these two things in parallel, and we'd like to figure out what that value is. So, in terms of equations, we can treat this just like two resistors in parallel, except we're using these complex impedances instead of our resistance values. So, Z equivalent is equal to ZR/ZC over ZR plus ZC. If you'd prefer, you could also do 1 over Z equivalent equals 1 over ZR plus 1 over ZC. That'll give you the same answer. It's just more math steps than this. So, whichever one's easier for you though. So let's do this. So ZR times ZC, I guess we should write down what ZC is first. So XC is 2K, ZC is going to be 2K times minus J, right? So that's 2K in the minus 90 degree direction. So ZR times ZC is 1K times minus J times 2K. Well, we can change that to an angle in a second. Divided by ZR plus ZC, so that is 1K plus negative is going to be minus J times 2K. Okay, we'll work our way to the left here. So in the top, we have 1K times 2K at an angle of minus 90 degrees. And this is, implicitly, this is 1K at an angle of 0 degrees, right? So when we multiply these together, we get the two angles added together. So it's 0 degrees plus minus 90 degrees, which is just minus 90 degrees. So this, we'll just leave there how it is. Divided by 1K minus J 2K. So on our complex plane, that looks like 1K in the x direction and minus 2K in the, x direction, in the real direction, and minus 2K on the imaginary axis. So this is the minus J direction. And that is supposed to be a right angle, and this is our total complex number. So in order to figure out, in order to combine it with this in the denominator, if we're dividing, we want to get this in polar coordinates, right? Because then we can subtract the angles and divide the magnitudes. That's how we do that. So we need to find out the angle of this. That turns out to be pretty easy, right? We have a triangle that looks like this. We want this angle. This side is 1, this side is 2. So that's the inverse tangent of 2. And that is 60-something degrees, 63.4 degrees. And looking at our diagram, you can see that it is in the negative direction. So our angle for this whole thing should be minus 63.4 degrees. The magnitude here, we just get that from the Pythagorean theorem, right? 1 squared plus 2 squared is 5. So this side is the square root of 5. So we could write the square root of 5 here, or we could write down what that is. That is 2.23. And these are kiloohms, so I also should have a K there. All right, we're almost done. So one of our K's is going to cancel, so we're going to end up with overall units of kiloohms in the top. 1 times 2 divided by 2.23 is going to give us 0.894. So that's 0.894 thousand, which is going to be 894 for this whole piece. Then we have our angles. So this is at an angle of minus 90 minus 63.4. And so that is going to give us an angle of minus 26.6. Oops, 26.6 degrees. So that is our final answer. So this these two in parallel are equivalent to a single impedance that is 894 ohms with a complex angle of minus 26.6 degrees. Note that this particular impedance we could get another way. Like these two in parallel are equivalent to two other things in series, and we won't find out what the values are, but I'll just draw you the picture, right? So the result of all of this is that we have something that looks like 894 at minus 26.6. And so that's going to be equal to a resistor with this resistance plus a capacitor with that reactance in series. So we could figure out what those are if we really wanted. But yeah, so these two in parallel are equivalent to some other resistor and capacitor in series. We don't need to know that. That's just fun fact, I guess. All right, so let's do another quick example. Hopefully this video isn't too long after all that. So let's say that we have a inductor now. We haven't done a lot of capacitors and inductors together. And again, we have some AC voltage source, and we have a capacitor in parallel with an inductor. And now I just decided that we would have actual values. So this is 1 microfarad, and this is 3 henries. So that's a pretty big inductor. And let's say this source, instead of getting the frequency F, let's just make it nice and round numbers. Let's say omega is 1,000 radians per second. So that's like 160 hertz roughly, or something like that. Okay, so what are these two equivalent to? Well, we need to figure out what their impedances are, right? So we have a capacitor, we have an inductor. The capacitor impedance is 1 over omega c in the minus j direction. So that is equal to 1 over 1,000 times 10 to the minus 6th, right? 1 microfarad. So this is 1,000. I forgot my minus j. So this is equal to 1,000 in the minus j direction, or 1,000 at an angle of minus 90 degrees. Our inductor is equal to j omega L, so that is j times 1,000 times 3, so that is an easy one, j 3,000. So this is 3,000 at an angle of plus 90 degrees. All right, so if we're combining these two in parallel, C equivalent is still the 2 multiplied over the 2 added. So ZC times ZL, so that's going to be 1,000 at an angle of minus 90 times 3,000 at an angle of plus 90, divided by ZC plus ZL, so that is going to be 1,000 in the minus j direction, or minus j times 1,000 plus j times 3,000. All right, so we can simplify this rather easily. So 1,000 times 3,000, their angles are going to cancel, right? Minus 90 plus 90, those are going to just give us an angle of 0. And so we have 1,000 times 3,000 in the top. I guess that's 3 million. I'll just write that. 3 times 10 to the 6th in the top, divided by, so we have j 3,000 minus j 1,000. So that equals j times 2,000. And now we're almost done. 3 times 10 to the 6th divided by 2,000. So ignoring the angle here. Well, I guess actually let's be careful and not skip any steps. Okay, so this is j times 2,000, right? So that's the same as 2,000 at an angle of plus 90 degrees. This in the top, we didn't write it because it went away, but really, 90 and minus 90 give us an angle of 0 degrees. So when we divide these, we get 0 degrees minus 90 degrees. That's going to give us an answer with an angle of minus 90 degrees. And 3 million divided by 2,000 gives us 1,500 ohms. So this is our final answer, 1.5 kilo ohms. We could also write this as 1,500 in the minus j direction, right? So, what is the conclusion from all that? I mean, we found the answer, so we could replace these with a single impedance at this frequency equal to this. But notice here that this is equivalent to a single capacitor replacing those two. A single capacitor with a slightly different value of the capacitance, but not super different. Okay, so what is the point of all of that? This is only true at this frequency, though, right? If we change this frequency, then the relative size of these change, and the relative size of these change, and we end up with some different number that is not just like, if we tried to replace these with just a capacitor and change the frequency, we would get a different answer. So we're not, we're getting a impedance the same as a capacitor at this particular frequency, but that whatever that capacitor value is will not be the same at other frequencies. So as the frequency changes, things are going to shift around, and we're going to do some kind of frequency dependent analysis in some future lectures. So we'll talk about exactly, how these quantities change and how their relationships change as we change the frequency of our voltage we're applying.